Bismillah ar-Rahman ar-Rahim. My name is Tahar Juwad, or in Arabic, Juwad Tahir. We are currently in Malaysia, Saturday, 10th September 23, or in Arabic, Al-Ahad, 10 September 23. So I am here in this video to introduce a module called Numerical Methods as a first course for my channel, Tahar Scholar, on YouTube. I'm here in Malaysia actually to launch this channel. I studied in Algeria. I obtained my ingénieura in mechanical engineering in 1995, and then my magister in 1998 in actually computational mechanics. And I was also a lecturer in the University of Boumerdès. Boumerdès is in the north of Algeria from 2011 till 2023. I just resigned a few days ago. So to focus on this channel. So the contents of this module is summarized here in 6 chapters. Each chapter is different. Each chapter has a different topic, completely different from the other. So the first chapter, the root of an equation. Chapter 2, a system of linear equations. Chapter 3, ordinary differential equations. Chapter 4, data interpolation. Chapter 5, definite integrals. And Chapter 6, least squares regression. In this introduction, I will, in the first part, I will explain the difference between numerical methods and analytical methods in mathematics. Then in the second part, I will go through each chapter, briefly of course, to give you an idea of the topic, the problem to solve, and an example, and the methods we will study to solve that problem for each chapter. Then in the third part, I will talk about how I designed this course and how I intend to deliver it through this channel. So there will be lectures, tutorials, and practicals. And finally, I will give some references. You don't need to buy any book or any software to follow me in this course, in this module. In American English, they call it a course. In British English, they call it a module. So I taught this module for several years in the University of Boumerdès, but in French. We say also in French, module. So let's start this introduction. So our module, Numerical Methods, first course, Introduction. In the first part, Numerical and Analytical Methods. So we want to see the difference between numerical and analytical methods through an example. So let us, for example, write a polynomial of second order, x squared minus 3x plus 2 equals 0. Find x. This is a well-known problem. We know how to solve it from high school. We first calculate the discriminant, determine the discriminant from the coefficients of the polynomial, b squared minus 4ac. This is a, this is b, this is c. So a is 1 in our case, b is minus 3, and c is 2. And if the discriminant is positive, we have two solutions. If it is equal 0, we have one solution. The parabola representing the polynomial is tangent to the axis. And if delta is negative, the parabola is either over, the whole parabola is over the x-axis or below it. So there is no solution, no real solutions. So in this case, we have delta equal minus 3 square minus 4 by 1 by 2. And we find it is equal to 1 positive. So there is actually two solutions, x1 and 2. And we know the formula equal minus b plus minus square root of delta all over 2a. And when we replace delta a and b by their values, we obtain, for plus, we obtain 2, and for minus, we obtain 1. So x equal 1 and x equal 2 are the solution of our polynomial equation, second order polynomial equation, are the solution of our equation. Okay, this is analytical mathematics. We manipulate a formula. The solution is expressed in form of a formula. This is analytical. This is an analytical method. Okay, so let's say this is one first point. The second point, let us see the following equations. Exponential of minus x, all minus x equals 0. Find x. Or, for example, sin x, I mean, in French we say sinus. Sin x minus x squared equals 0. Find x. So equations here are more complex, more difficult. And another example, logarithmic, Neperian or natural, of x plus 1 over x minus 1 minus square root of x equals 0. Find x. So it's the same topic, an equation. You are given an equation and you are asked to solve it to find the unknown x. But here the equations are more complex, more difficult, etc. of course. Here there is no analytical method. So for the majority of problems, we can't solve them using an analytical approach, an analytical method. We need here a numerical method. Like the ones we will see. There is actually several methods for each topic, and each method has its pros and cons. So we have to, of course, to choose one or two methods to teach. We will not see all the methods for each topic, of course. But this is the difference between analytical method and a numerical method. Numerical method is more general and can solve all kinds of problems for a given topic that analytical approach cannot solve. Another important feature is in numerical method, you will never find the exact solution. There is always an error. Numerical methods always has an error. Always has an error. While the analytical method gives us the exact solution. So this is the difference. Let's move to the second part. To the second part. To the contents. And we start with chapter 1. Chapter 1 is the root of an equation. So chapter 1. The root of an equation. Let's see the problem, the example, and the methods. So, first of all, the problem. Before to solve the problem, you must know the problem. So, first of all, the problem. Problem is to solve fx equals 0. F is a function of x, any function of any complexity like this one's. And you are asked to find x in a given interval. These methods we study in this chapter need an interval, not just the equation, but also an interval, valid interval that contains one single root. If the equation has several roots, you should give the interval that you need for each root. It doesn't work if you give an interval containing several roots. Okay, all the methods in this chapter need an interval containing a single root, AB. So, or we can also formulate, this is the analytical form of the problem. We can also present it graphically, or graphically, let's use another color. So we have the x is x and the y is x, the abscissa and the ultimate. And we have the curve of f crossing the x-axis. This is the curve of f. This is the curve of f. And this is the root we are looking for between A and B. This is the root of the equation. Let's call it XR. And let's write it star to say that it's the exact root. As we see later, there is the exact or the true root and the false root. So star means exact and R means the root. So in other words, graphically, the root we are looking for is the intersection of the curve of f with the x-axis. This is what we are looking for. This is the problem. And I can give an example, of course. For example, that we will solve later in the chapter. So this is just an overview. Exponential of minus x equals 0. Find x in the interval 0, a equals 0, and b equals 1. I have already, of course, this is f of x. I've already drawn the curve with MATLAB, using MATLAB, and find out that the interval that contain the root is 0, 1. So we cannot. This is the problem. This is part of the problem. It's not enough to give the equation. You need also to give the interval. How? You have to draw the function and find out where it cuts, where the curve cuts the x-axis. So visually, you have to give the interval. And the third point is the methods. We have here, there are several, maybe 6, 7 methods in 2 categories. They are divided in 2 categories. Bracketing methods, and open methods. Because of time, we will focus only on one method. And in the last lecture, each chapter will have between 3-4 lectures. The last lecture, I will give an overview of all the methods. But in the chapter, we will focus only, in this chapter, we will focus only on one method called Abu Kamel method. Abu Kamel method, or Abu Kamel's method in the 19th century or 3rd Hijri century in Egypt. It's also called regula falsi, or the false point method. No, it belongs to this category, bracketing method. But as I said, I will give an overview of the pros and cons of each method in the last lecture. But all of the focus will be on this method. So this is for chapter 1. Let's move to chapter 2. So, chapter 2. System of linear equations. So let us see the problem. First of all, the problem through an example. Let us suppose we have 3 variables. So x, y, z in a system, 2x minus y plus z equals 0, first equation. Then minus x plus 3z equals 0. Then 1.5x minus 2y plus z equal 2.5. So we have 3 equations with 3 variables. The number of equations must be equal to the number of known variables. We are looking to find x, y, and z. So the x, y, and z are the unknown. We call this linear equations because there is no square or power, logarithmic, sine, etc. It's plain simple, plain linear. We can rewrite this system in a matrix form, like this. Matrix with 3 columns, column for each variable, and 3 lines, 3 rows, for each equation there is a row. This is called row. Rows, row 1, 2, 3, and column 1, 2, 3. This is the matrix A. In the matrix A, we put the coefficients for each variable. So we have 2, minus 1, 1.5 for x, and minus 1. Here there is no y in the second equation, so 0, and minus 2, 1, plus 3, and 1. Multiplied or dot. In linear algebra, we call that dot product or inner product of x, y, and z. The unknown variables equal the vector b, call it vector b, 0, 0, 2, 0 or minus 1 here. I have made a mistake. Minus 1, minus 1. A small mistake. So we call this x, the vector x, and this the vector b. A and b are given. We are looking to find the vector x, the variable x. So this is the matrix form or format of the problem. Or more generally, given the inner product a by x equal b, find x. With a belonging to the space R, m by m, means the number, the elements of the matrix are real numbers, and it has m rows and m columns. It is a square matrix. So the matrix here must be a square matrix. The number of rows equals the number of columns, because the columns represent the unknowns and the rows represent the equations. So this is, and x belongs, the vector x belongs to R, m, and b the same belongs to R. So it has only one dimension, here 2 dimension. Some people note a vector like this with an arrow. You can also write it like this, and it represents, in this case, x, y, z, or you can also write it x1, x2, x3. First element, second element, the third element of x. This is more general notation. This is limited when x is small. But in general case, you have m element, x1, x2, x3, x4, etc. till xn. So this is our problem. We give you a and b, find the vector x. How to do that? There is, let's see, 2. Here the problem and examples are in the same section. So to the methods. There is, of course, several methods. This is a big topic, numerical linear algebra. But in this first course, we study only the basics, the foundation. And 2 methods are very important The first is the Cramer's methods. Cramer's method, I mean, and Gauss's method. Cramer is a Swiss scientist and mathematician, Swiss, in the 18th century. And Gauss is very known in mathematics and in physics. Has many contributions. He has many contributions to this field, numerical methods and mathematics in general. He's a German in 19th century. I think he has written a book when he was only 20 years on number, I think, number theory. It's very known, Gauss. So the Cramer method is Cramer's method is suitable for 2 or 3 equations with a pen and calculator. It's very easy to use the Cramer method. It's easier to use Cramer method than Gauss method when you have only 2 or 3 equations. So it's suitable for 2 or 3 equations. More than 3 equations, it becomes really difficult to use it. Gauss is more general, can deal with 3, 4, 5, 1,000, 1 million equations. Of course, when you program it, you can use it for small number of equations with a pen and calculator, as we will see in the chapter, or we can implement it using MATLAB, and we can then use it to solve any system, any dimension. So that's an important note. Cramer is limited. So we will focus on Gauss method. There is, of course, as I said, there are, of course, other methods, direct and indirect methods, but we will not go. This will take a whole module if we study all the methods. Module called Numerical Linear Algebra. So here we focus only on these 2 techniques. Okay, this is for chapter 2. Let's move to chapter 3. Chapter 3. Ordinary differential equations, or shortly ODEs. Ordinary differential equations. What is that? As usual, problem, example, and methods. So first of all, the problem. So let us suppose we have a variable, dependent variable, that is a function of an independent variable. Y is called dependent variable, and X is the independent variable. An ODE differential equation, you have not directly the y in the equation, but its derivative, its evolution, or its variation with respect to x. So in an ODE, you have y prime equal a function, an expression of y and x. You are given an equation where the derivative is a function of the dependent and the independent variable. And it is called ordinary because there is only one single independent variable. If a variable depends on, let's say, 2 or 3 more variables, then it is called partial differential equation, not ordinary differential equation. That's the meaning of ordinary. Ordinary means simply that there is one single independent variable. And it's not enough to have only the variation of y. You need also to know the value of the value of y at the beginning of the interval. So y0, the value of y at x equal x0. And you are asked to find yx in the interval x0, the first value in the interval, the beginning of the interval, till xn, the end of the interval. You call it xn or L or whatever you want. So you have the derivative, the initial value, and you are looking to find not a number like in chapter 1, not a vector like in chapter 2, but a function. The unknown here is a function. This is first order ODE. First order because we have only the first derivative of y. This is the problem we have to solve. Let us see an example, a concrete example. An example my notes. So let's see a concrete example. Y prime equal 1 plus x square root y. And we give the initial condition y0 equal 1. Find y, x in the interval x belonging to 0 till 0,5. So we are asked to find y with respect to x that satisfy this first order ODE, its derivative. This is fy to x, it's an expression where you find y, the dependent variable, and x, the independent variable, both. And you are given the value of y at the start of the interval. This is the initial condition. Okay. We can also present the problem in a graphical way. I show you that. So let us suppose we have the x-axis and the y-axis. This is x0, the start of our interval, and this is xn, the end of our interval. We want to know our function in this interval. And we are given the first point, y0, the image of x0. What we are looking for is the curve, the whole curve of the function, the whole curve is an unknown. And as we will see later in this chapter, we actually look for not the curve is continuous, there is an infinity of points. It's impossible, of course, to find all the points. We will find a sequence of points close to the curve that will build a polygon that approximate our function. How to do that? We will see that in this chapter, later, of course, in this chapter. So the methods that we will study to solve this problem. First method is Euler's method. Euler is the pioneer in this field. Is a very well-known mathematician and also physicist or scientific researcher in the 18th century. He's also Swiss, like Kramer in the 18th century. He was a friend of Bernoulli, and Bernoulli was also very well known. But Euler method is studied only or is taught only for pedagogical reasons. It's not accurate. So we will study a modification of Euler due to Hoyne's method, who is a German in the end of the 19th century. I think he has published this method in the end of the 19th century. And finally, two mathematicians, Runge and Kuta. Runge-Kuta method. Runge and Kuta propose several techniques in different orders. We will focus on Runge-Kuta, the fourth order. There are of course several details. That's why there will be 3-4 lectures for each chapter. This is just an overview, what you will expect, what you can expect to find in this chapter. So we will study others, Hoyne, Runge-Kuta. Runge-Kuta are also German in the same period of Hoyne. Let's say start of the 20th century. And that's it for chapter 3. Let's move on to chapter 4. Before to move to chapter 4, there is some remarks here important. The first, so some notes. We could use the same methods with a slight modification to solve not only one single first order ODE, but also a system of first order ODEs, that is several ODEs. We will also see how to solve a second order ODE in this chapter by reformulating the second order ODE into a system of two first order ODEs using exactly the same methods, not a new method. And actually, any higher order ODEs can be solved by reformulating it in a system of first order ODE. So the methods here are very powerful to solve any kind of ODEs. Another note important also, So let's say this is one, first note, number one. Number two, in many problems, the independent variable is t, not x. So the ODE could be given like this. Y point means the derivative of y is a function of y and t. Find yt. T is the independent variable time. In physical problems, has the meaning of time. But in mathematics, any independent variable, that's why we call it x, it has not to have a particular meaning. So y0 is given at t0. Find y in t0. Yeah. You can also use, or you find that in textbooks. It's not another ODE, it's the same ODE, but the independent variable is time. Another example of second order that we will solve in this chapter, the well-known case of the pendulum, very known pendulum. Let's use another color with a rod. As the rod has negligible mass, and at the end there is a mass m that swing. There is a length of the rod is given, and the dependent variable, the function we are looking for, is theta. It's the angle that the rod makes with the vertical line, which is the initial position, or the position of the pendulum at rest. It will oscillate. So theta in function of time. When we study that in physics, we find the following second order ODE. An example of second order ODE is theta second that modelize the physics of the pendulum. Theta second derivative with respect of time of theta plus g the gravity acceleration over L sin theta equals 0. Find theta with respect of time. Now you see there is no m. M is not expressed in the ODE. Whatever you can change the mass, you will find the same moment. It depends only on L. Okay. This is an example of a concrete example of second order ODE that we will solve in this chapter. Let us move to chapter 4. So, chapter 4, data interpolation, another topic completely different. Interpolation. So let us see the problem here. First of all, one example. So in this chapter, you are given data in a tabular form. The abscissa, the xi, and the ordinate yi. For example, 4 points. And you are asked to find a polynomial that passes exactly through these 4 points. So if you have 4 points and equal 4, the number of points, then we must find a polynomial of order 3, the number of points minus 1. The order of the polynomial, the order of the polynomial, the order or the degree, the order or the degree of the polynomial must be equal the number of points minus 1. Always, always. So if you have more points, the degree of the polynomial will increase, of course. So in this case, we have 4 points, any value, and you have to find the polynomial that passes exactly by these 4 points. So a0 x plus a1 x, a0 I mean, plus a1 x plus a2 x squared plus a3 x cubic. Or we can also write it a0, a1, a2, a3, the vector of the coefficients, dot 1 x, x squared, x cubic. Coefficients are known. The problem is to find them. How we will see how. So graphically, this is analytically, graphically, this is the x-axis, the independent variable, and the y-axis, the dependent variable. But you don't know function that maps x to y. You only have a finite number of points, and you are looking for a function that maps them in the form of a polynomial. So let's say we have here point 1, point 2, 3, point 4. Let's call this one x1 and this x2, this x3, and this one is x4. So the xi I from 1 till 4 have not to be in an ascendant order, have not to be in the ascendant order. So we have 1, 2, 3, and we come back x4. And they have not to be equally distant. But the value of y must be precise. This is important. The value of I from 1 till 4 must be precise. The error on them is very small. And we are looking for a polynomial of order 3, is a cubic here, that passes exactly by the 4 points. This is the curve of G3. This is the unknown that we are looking for through the coefficients. If we know the coefficients, we know the polynomial. So this is the problem. Now let's see the methods. Check notes. So there is actually two categories of methods. The first category is to find the whole polynomial, one single polynomial that crosses all the points. And here we'll study Newton's interpolating polynomials. This is a note on the data, input data. To be observed when you deal with interpolation. As we will see later, there is another problem close to that, but different. So, Newton's interpolating polynomials. Newton, of course, is well known as a British, the genius, physics and mathematics, numerical methods in calculus. So British in the 17th century. And we see also Lagrange's. Lagrange's is a slight modification actually of Newton's method. Lagrange's interpolating polynomials. And it is French. It is actually an Italian, but then it changes citizenship to become French. In the 18th century, he is also very known in, I think, in elasticity and mechanics. 18th century. So in these two methods, we will look for one single polynomial that crosses all the points, all the given points, data points. But when the number of points is big, the method is no more accurate. So some people have devised another technique called, let's write it here, of space, spline interpolation. It is actually a piecewise interpolating polynomials. For each interval, we have a polynomial, I mean. For each interval, we have a polynomial, not one single polynomial. It is piecewise interpolating polynomials. So it's more accurate and suitable when you have a large number of points. And it is due to, we'll see of course the details in the chapter, just an overview to see that there is two categories, first and the second. It is due to Schoenberg, I think, yeah. IJ, see my notes here. IJ, my notes are in front of me. Due to IJ Schoenberg in 1946. Schoenberg is American, and let's write here American. He's, I think, from Romania, but he immigrates like many Europeans in that time war, after the Second World War, to America. American. And he has published many articles on spline. Splines are used in a more sophisticated formulation of spline called B-spline NURBS, non-uniform rational B-splines in graphics. But here, of course, we are We are in a foundation course, first course, study the basic supply interpolation. And as I said, it interpolates. It also crosses the 4 points, but by interval. Polynomial is built by interval, with some constraints, of course. That's it. That's it for chapter 4, data interpolation. Let's move forward with chapter 5. So, chapter 5, definite integrals. The problem. Problem here is to calculate the integral of fx function, continuous function, fx dx from a to b. And we find a number. How to do that numerically? This is equivalent also. This is the analytical formulation. This is equivalent to, let's change color, the axis x and the y-axis. This is A and this is B. And let's suppose our function is like this. So the curve of f is given, a and b are given. The integral of f between a and b is actually this area. Choose another color. This area between the curve and the x-axis and bounded by a and b. This is I, the area. The area is actually the integral I that we are looking for. How to do that numerically? You can, of course, when the function is simple, integrate it analytically and find the result. But often the integral is very difficult to calculate. So the methods we study in this chapter makes it possible to calculate it numerically, with an error, of course. So before to move to the methods and to see an example, let's make a difference between definite, or let's notice the difference between definite and indefinite integrals. F is called the integrand. The integrand, I mean. The integrand with A, the integrand. So, this is important because there are people who are confused between definite and indefinite. Definite integral is a number. As I said, graphically it means the area between the curve and the axis. But indefinite integral is actually a function with respect of x that is equal to the integral of fx dx. It is a function such that it is called the primitive, or the antiderivative. Derivative. The antiderivative. Why? Because this is equivalent to say that f prime of x equals fx. These are equivalent. These two formulations are equivalent. The primitive of f is such that its derivative is the integer. And we know that this is an ODE. This is a simple ODE. You have the derivative of the unknown variable, fx. F is the dependent variable, x is the independent variable. We are looking for the primitive such that it satisfies this ODE. And it is a simple ODE because the function, the expression of the derivative, depends only on the independent. In the general case, you find the independent and the dependent. You find the x and f. But in this case, you have only x. So it is actually a simple ODE, first order ODE. So looking for the indefinite integral is equivalent to solve an ODE where the dependent variable is the integral, is f. So are two different. This is a function and this is a number. In this chapter, so we focus on the definite integral. Let's give an example. You are asked to calculate, find e such that it is the integral of ex squared between 0 and 1. Or graphically, is the axis. You can draw it with, for example, MATLAB. Via 1, 2, 3, 1, 2, 3, and for 1 we have e between 2 and 3. Something here and here. And our curve should be like this. Exponentially grows exponentially. It's not a parabola. And the integral is this. Area between 0 and 1. This is 1, 2, 3, the x-axis and the y-axis. And this is the curve of e exponential of x square, exponential of x square. So this is what we are looking to calculate numerically. The methods. How we do that? There are two types of methods. In the first type see the trapezoidal method. Trapezoidal method and the Simpsons, don't know exactly the pronunciation, I think Simpsons method. Simpson is a British, Thomas Simpson, British in the 18th century. In this category of methods, we use actually a strip to calculate. So this is This is the curve of the integrand. This is A, this is B. This is what we are looking to calculate. The area. This method are based on a strip. This we calculate, there's a formula for this strip, has a given width h, and the problem is here, how we interpolate this part, how we approximate this part. Trapezoidal or Simpson's method are based on how we interpolate a strip, and then we add the strips to obtain the whole area. This is the idea. Of course, there are many details, but this is the idea. It's based on strip. The integral, the area, is a sum of a finite number of strips with a given width. The second type is due to Gauss and Legendre. Gauss, we have already seen Gauss, German, well-known mathematician, and Legendre is a French. Gauss and Legendre method. It's important to know people, at least to have a brief history on the people behind these methods, behind this knowledge, that they have contributed to the human knowledge. It's important to know that. So Gauss-Legendre method. Legendre is a French. A.M. Legendre. French in the 18th century. Here, the idea is to use, this is the curve of f, the integrand, and these are A and B. But here we don't use a strip. This axis, we use a number of points that have a particular distribution called Legendre distribution. Legendre is behind finding this kind of points. They have particular properties. They are not randomly, of course, properties between A and B. And for each point, we associate a weight, a given weight, a given number, to emphasize its importance, its contribution to the integral. So a point with small weight will contribute small value of its image. So we evaluate f at this point and we multiply it by its weight, plus the image at this point and multiply it by this way, and so on. So it is based on a distribution of a set of points with weights. While here it is a sum of the area of strips, of a finite number of strips. So these are the two category of methods we will study in this chapter. Now let us move on to the last chapter, chapter 6. So, chapter 6, least squares regression. This topic is close to the interpolation, but at the same time completely different. So we are given also an input of data points, but generally the number of data points is big, endpoints. We have the x, the axes and the y's, the abscissa and the ordinate, the independent variable and the dependent variable. And they must follow the following constraints, or they must satisfy the following constraints. The xi must be precise and in ascendant order. Yi have not to be precise, and generally are not precise, are random. That could be, for example, from an experiment. You measure temperature, y is temperature, y represents temperature, the dependent variable, and x is time. You measure the temperature of an object, for example, or the room with respect to time. And the results of the experiment are not precise, of course. It depends on the equipment, etc., etc. Or, for example, you measure the force applied to a spring with respect to the length of the spring. So to find a relationship between the force applied force and the length of the spring. So this comes in general, input data comes in general from an experiment. That's why the dependent variable, the y, is not precise. But xi must be in ascendant order. They have not to be equally spaced, but they have to be in ascendant order. And the problem is to find a line or a polynomial that is close to each point, close but not passes through each point like in interpolation. Here the line or the polynomial has not to pass exactly through each point. Let's see that graphically. I have presented the sample of points that the trend is like a line, and we are looking for a line, for that line, that follow that trend, that is close at distance between each point and the line is optimal. This vertical distance is optimal for each point. Find this line. How we see that in this chapter? It can be a line, it can be a parabola if the trend of the points are a parabola or cubic. So we will, in the methods, we will study linear regression and polynomial regression. They are actually, it's the same technique, but polynomial is a little bit more difficult. There are more in this to this topic, but this is what we will study at this level of a first course. Who is behind these methods? Gauss and Legendre are the first to publish on least squares regression. But the term regression has been coined by Gallon, F. Gallon, in 1885, many years after the publication of Gauss and Legendre. He was studying the length of sons with respect to their parents and see the regression of the length towards the mean. And you call it regression towards the mean. So the mean of the lengths. So it is, albeit it is named by Gallon, but the research, the mathematics behind least squares regression is due to Gauss and Legendre. That's it for the contents. Let's move to the third part, how I have designed this course. So, third part, design of the course. So for each chapter, there will be 3 to 4 lectures and 3 to 4 tutorials where we do exercises with a pen and calculator, need a calculator, and 2 or 3 practicals where we learn how to implement the algorithm or the methods we have studied in lectures and practiced in tutorials. We will use MATLAB. So before the first practicals, we will do an introduction to MATLAB. Introduction to MATLAB. MATLAB is a very introduction to MATLAB. We will do two practicals for MATLAB. MATLAB means matrix laboratory. We will not use actually MATLAB. We will use Octave. Octave is a free version of MATLAB. Is compatible with MATLAB. What you write in MATLAB will works on Octave and vice versa. But it's free, completely free. You don't have to pay anything to follow the practicals. So I will show you how to use Octave and how to program in MATLAB language, because we need that in every chapter. Every method can be implemented. In fact, the success of numerical methods is due to computer science, to programming. And MATLAB is very popular in numerical analysis, numerical methods. So we will learn how to use MATLAB through these practicals. So each lecture or tutorial or practical is a session, is a video. So each session or video I will try to not exceed 1 hour. So each session will last 1 hour. Nothing more for 1 hour. When I used to teach in the university, actually the session, but with students in a classroom, lasts about 1 hour, it lasts 1 hour and a half. It's standard in Algeria. Each session, being a lecture or tutorial or practical, lasts 1 hour and a half. But here I'm talking alone with you, but alone. So I will try to not exceed 1 hour. For uploading, I will upload at the end of the week, Friday and Saturday of each week. So the first one or two videos per day. I will upload first week the lectures. So the first week the lectures, 3 or 4 videos Friday and Saturday. 1 video Friday, 2 videos Saturday, or 2 videos Friday and 2 videos Saturday. So all the lectures pertaining to chapter, for a chapter, all the lectures Friday and Saturday. And then the next week, the second week, I will dedicate to tutorials. And the third week to practicals. So that's the plan. I will try to upload every week. And with this plan, we need 3 weeks for each chapter. So for each chapter. So conclusion is we need about 6, because there are 6 chapters by 3 weeks, 18 weeks. That's about 5 months. We need 5 months for the whole module. For the module numerical methods. So it will take time, of course, to deliver all these videos, to prepare, etc. It will take time and energy, but you do not have to follow this plan. You can study, for example, the lectures, and then 1 day or 2 days later you study tutorials. Then you make a pause and you study practicals, depending of your study schedule. So you can organize. Watching these videos according to your study schedule, because everyone is different. You might be a student, you might be working, you might be a teacher, etc., etc. You might be an engineer and you want to revise maybe a particular chapter only, not the whole module. So it depends of each one. Everyone is different, but this is what I will do. I will deliver per week lectures, then tutorials, then practicals, and that's it for the design of the course. Let's move to references. I have 2 important, but you do not have to read them. It's a plus. If you have time, or you want to see more examples or other methods that we have not covered in this course, you can check 2 very good books. I have read somewhat old edition, but you can look, of course, in your library. You don't have to buy them. So we have first reference is the work of Chapra and Canal, 2 professors, and the title of the book is Numerical Methods for Engineers. The edition I have studied is 2015. It's very pedagogical and has a lot of practical examples in mechanical engineering, civil engineering, in chemistry, electricity, etc. Of course, simple examples of the level of first and second year. Not advanced. Because this course is numerical methods, is for student of first or second year. And the second book is by Burden and Fairs, or Fair, I don't know exactly the pronunciation, but with S. And the title is Numerical Analysis. I have studied the edition 2011. This book are republished and revised each like 5-6 years. So you might find a more recent edition. The book of burden and phase is more formal, more rigorous, and the algorithms are better presented. But is a little bit dry. It's not like has not the pedagogy of Chapra and Canal. Chapra and Canal, I think, is more pedagogical. So this is what I advise to read if you have time, of course. But if you follow me with in this channel, you don't need to read any book or to buy any software. You just follow me. But if you want more, of course, you can get MATLAB, student version maybe, or an academic version. And you can also find these books on your library, or ask your library to buy them. And that's it for this introduction. Please follow me, subscribe, and my next video, inshallah, next Friday. Next Friday, I will upload the first lectures, all the lectures of the first chapter. 3 or 4 lectures, Friday and Saturday. See you then, inshallah, and peace.